Hi everyone and welcome back to one more part on radiographic testing. So far we have learned about how the image is formed, okay, and we have also seen in last couple of lectures how the image quality is controlled and what are those parameters which control the image quality. Okay. So, now that we know how the image is formed, we can talk about the exposure as to how exactly the exposure is done, and what kind of things are used for exposure, and for a particular material of given thickness, what are the exposure parameters, particularly the exposure time, how it is decided. Okay. So, that is what we are going to discuss in today's lecture. So, first let us talk about how the film is loaded when you expose it for a particular exposure. Okay. So, in order to capture the image on a X-ray film, you need to take it to the machine, right, and you have to load it in the machine. But as you all know by now, these X-ray films are sensitive to light. If you expose the X-ray film to light, then they will darken, and once they darken, you cannot use them for capturing the image. Okay. So, when you take this film to load it into the instrument, this film has to be protected from light. Okay. And in order to do that, you need some kind of enclosure which will do this job of protecting the film from visible light. And that is why this kind of sample holders are used for loading the film first. Okay. This kind of sample holders that you see over here, okay, and this can be this is available, this kind of sample holders are available in different sizes depending on the size of the sample that you have, and it has a chamber inside. If you open it, you could see that, right, like this. Okay. So, you can keep the film inside this, and you could see there is a cushion for the film against scratching and all that. So, that the film is not damaged when you keep it inside. So, this cushion is provided for that, and you can keep this and then you can close this. Okay. Once you close this, this becomes light tight. That means, this will no longer be exposed to light. Okay. You could also see inside this cassette there are few more things. If you remember, we talked about intensifying screens which are used to enhance the image quality or to enhance the efficiency of image formation. And as I told you, the intensifying screens have to be kept right over the film. Okay. So, here you do not really see anything externally, but this still has an intensifying screen inbuilt inside this chamber over here. Okay. So, it has two walls, as you could see, the top one and the bottom one. Okay. So, in the top one, inside this black layer, the intensifying screen is inbuilt. Okay. It could be a metallic intensifying screen, or if you want to use those fluorescent salt intensifying screen, they can also be used as a thin coating on the top surface. Similarly, the bottom surface also, here just below the cushion there is a thin lead screen, so that you can address those backscatter radiation which comes from this bottom surface. And apart from that, this material, if you see, the material of this cassette is made of such a material which is low absorbing to X-rays, so that the X-rays can easily pass through it, and on this surface as such there is no attenuation to the intensity of the X-rays. Okay. So, this has to be made of a material which is low absorbing. For example, aluminum can be used. In fact, this cassette that you see over here, this is made of an aluminum alloy. Okay. So, this is what is being used for loading the X-ray film into the X-ray machine. You might have seen this while doing medical radiography also. They have a cassette like this, maybe a different size. This cassette is being held in close contact with our body when a body part is being imaged for medical radiography. Okay. Then on this the sample is kept on the top surface. Okay. So, right below this you have the intensifying screen and then you have the sample. Okay. So, if you remember we also discussed that the intensifying has to be in between the sample and the film, and it should be also there on the bottom surface, so that the backscattered radiation can be addressed. Okay, so this is one aspect of exposure as to how to load the film for a particular exposure. Okay. Now, when you take a sample and you do this exposure for capturing the X-ray image, what you control on the control unit is primarily the exposure time for a given tube voltage and given tube current. Okay. This tube voltage and tube current on the other hand can also be varied for a given exposure time. Okay. So, that means first you need to decide what should be the exposure time for a given tube voltage and a given tube current. Okay. So, this time would depend on what kind of sample you have, that means the material of the sample and the thickness of the sample. Okay. So, these are the two parameters which will primarily decide the exposure time for a given voltage and current. And in order to do that, you need a relationship which could be used to decide this exposure time based upon the thickness of the material. Okay. So, this relationship or the equation comes from two laws. One of them is this one that we have already discussed probably by now. The intensity is inversely proportional to the square of the distance. Okay. So, if I be the intensity and L be the distance, this will be the relationship between X-ray intensity and the distance between the source and the sample. Okay. And that is why this is known as inverse square law. So, this means for two different intensities I 1 and I 2, this will be equal to this. Okay. So, this is inverse square law, and the intensity is a direct output of the number of electrons which are impinging on the anode per unit area per unit time. Okay. So, that means the intensity is dependent on the tube current. Okay. And that is why you have this particular relationship, I is inversely proportional to exposure time. If the tube current is high, then the intensity will be higher, and as a result of that the exposure time will be lower and vice versa. Okay. So, this means I times T is a constant, or the relationship between the tube current I and the T is reciprocal, and that is why this particular relationship is known as reciprocity law. So, we have these two laws or these two relationships, reciprocity and inverse square. And these two can be combined into one in order to decide that exposure time. So, if you combine these two, it will give rise to this particular relationship. Okay, and this will tell you as you vary the thickness or the distance L, how the time t should vary, or if you vary the current for a given distance, then also how the time of exposure should vary. Okay. For example, if you have a distance of 1 meter and a tube current of 20 milliamps, and for a given material, let us say you have used an exposure time of 10 seconds. Okay. Now, if you change any of these, either the distance or the current, then the time will change according to this relationship that we derived just now based upon those two laws. For example, if you change L to 0.8 meter from 1 meter, then for the same tube current, the time needed for a similar quality of image, the exposure time for that will be because this varies as the square of the distance. So, for 1 meter it was 10 second and for 0.8 meter it will be 6.4 second. Okay. So, this is how if you vary the distance, the time will vary according to this relationship. And if you change the current also from 20 milliamps to 16 milliamps now, and the distance also is changed to 0.8 meter. So, for that case, when you change both distance and the tube current, then again from this particular relationship you can find out what will be the time, and in that case it will be 8 seconds. Okay. So, like that based upon this particular equation, this is how we can find out for a particular tube current and particular sample to source distance what should be the exposure time. But here this is about the distance between the source and the sample. But as I said before, this will also depend on the sample thickness, and when you take into account the sample thickness also, then you need to use these calibration charts which are obtained for different sample thicknesses, and this has to be supplied by the manufacturer of the instrument who has to do this calibration and provide you this kind of exposure charts for different sample thicknesses for a particular sample to source distance. Okay. So, generally the sample to source distance is kept at 1 meter, because this is convenient to use when you convert the exposure time for some other distance. So, this chart is in between this exposure chart or the exposure plots that you have. It is in between the exposure So, this is in terms of times the current into the exposure time, and this has to be calibrated for a particular material against the thickness. Okay. So, it can be done for example, on a steel sample for a fixed sample to source distance of 1 meter, and then you vary the thickness and obtain the data, and when you plot the data at different tube voltages, this kind of curves will be obtained. For example, if you are using 100 kilovolt like this, so it has to be done at different tube voltages and different sample thicknesses over the entire tube voltage that the instrument offers. Okay. Like this. So, when you do the radiographic testing, before you load the sample into the machine, you should first refer to these exposure charts which are provided by the manufacturer for that particular instrument. Okay. And you then see what is the thickness of the sample, and based upon that thickness and the tube voltage that you are using, you see what is the exposure needed. Okay. So, this exposure could be in terms of milliamps minute or a milliamps second, and this tube current is already known. It is generally in the range of 5 to 10 milliamps for most of the machines. Okay. And once you know this, then you simply divide this by the tube current, and from that you will get the time. Okay. So, this is how, based upon these exposure charts, you have to first decide the exposure time for a given material of a particular thickness. Okay. So, this is done for steel, but this has to be obtained for other materials also, and you may or may not have this kind of plots for all the materials, but what you can have for convenience is you can have this conversion of steel to any other material thickness. So, you can convert any material thickness to an equivalent steel thickness. So, if you have a sample made of any other material, that thickness has to be converted to an equivalent steel thickness, and then that thickness can be used for this kind of charts which are generated for steel samples. Okay. I can give you example for that. Let us say you have a composite plate, or before that just let me tell you what are the conversion factors for different materials to convert their thickness into an equivalent steel thickness. Okay. Let us say copper, aluminum and lead. For these three materials, if you want to convert their thickness into an equivalent steel thickness, that would depend on what is the X-ray energy that is being used. So, we can see it for different X-ray energies. So, for 300 kilovolt, for example, for copper, the conversion factor would be 1.5. Okay. Similarly, for aluminum it is 0.19, and for lead it is 17. Okay. So, you could see depending on the material it varies over a wide range. So, let us say for example, if you have 10 centimeter of the copper, that will be equivalent to 15 centimeter of steel thickness. Okay. Then as you decrease the X-ray energy, this would also decrease like this. For copper it will be 1.45 at 250, 1.4 at 200 kV and 1.3 at 150 kV. Similarly, for aluminum it is 0.17, 0.16 and 0.12. For lead it is 15 at 250 kV, 13 at 200 kV and 11 at 150 kV. Okay. So, based upon this kind of conversion charts which are readily available, the thickness of any material can be converted to an equivalent steel thickness, and then you would be able to use those exposure charts which are obtained for different thicknesses of steel. Okay. Yeah, we can take an example as I was telling you. Let us say you have a composite plate which is made of 3 different metal sheets: aluminum 1.5 mm, copper 3.6 mm and lead 0.9 mm. Okay. Okay, so, let us say you have a composite plate like this, which has these 3 layers made of 3 different materials having this kind of thicknesses. Okay. So, for a tube voltage, let us say 200 kilovolt or 250 kilovolt, if you want to decide the exposure time for a given tube current, then you first have to convert the thickness of this particular plate into a steel thickness. So, the thickness of this plate is 1.5 plus 3.6 plus 0.9, which is 6 mm. Okay. So, this 6 mm thickness of this material has to be converted into an equivalent steel thickness for a given X-ray energy or tube voltage. And we have already seen what are the different conversion factors for different materials for these 3 material at a particular tube voltage, let us say 200 kV. So, just now we saw that at 200 kV for copper, aluminum and lead, if you convert their individual thicknesses. So, in this case we have 3.6 mm of copper, and for copper the conversion factor at 200 kV is 1.4. So, that will be the equivalent thickness for copper. For aluminum it is 1.5 mm and the conversion factor at 200 kV is 0.16. Similarly, lead is 0.9 mm and the conversion factor is 13. Okay. So, this will give you the thickness at a particular voltage. So, if you calculate this will be 17 mm of steel. Okay, so, this is how any material thickness can be converted into a steel thickness when you want to use that exposure chart for calculating the exposure time. Okay. So, with this we come to the end of this particular lecture. So, for today this is all I will have. So, I am going to stop here today, and I am going to see you again next time for rest of the things that we have for this particular technique. So, I am going to stop here today. Thank you for your attention.